So I'm Mary DeSalt, and also on the line are Tim Rue.
Hello, everybody.
Who is the Senior Informal Education Specialist at the Space Telescope Science Institute and on the Universe of Learning team. Also from Space Telescope is Brandon Lawton, Dr. Brandon Lawton.
Hello. Who
is an education and outreach scientist, and in the room with me, but not quite behind me, sort of on the line with me, is Erica Wright, whom some of you know from our past Affiliations collaboration with Youth Capture the Colorful Cosmos. And then from the Affiliations office in Washington, we have on the line two of these three contacts for you guys. Patty Artiga is on the line and is kind of the program coordinator for this partnership. And Caroline, I think you wanted to give a welcome, so I'm going to give you a moment.
Hi, yes, I just wanted to say welcome everyone. Thank you so much for participating and being a part of our informational call, which took place a couple of weeks back, actually a couple of months back now. And we're very excited to get underway with this program. Mary and the entire team at SAO has been a fantastic partner with us for the past maybe 4 or 5 years already. So we're excited that we're able to work with her and her team on another project. And this is a separate project, but it's funded by NASA, and we're excited about the contributions of our affiliates in this program. So thank you again.
Great. So thanks, Caroline. So Brandon, if you could go to the next slide. The Universe of Learning is a NASA-funded partnership among many science organizations that work on NASA astrophysics research, and many of whom also do some education. And it's led out of the Space Telescope Science Institute, where Tim and Brandon are, and Denise Smith is the principal investigator of the whole overall program, which has many pieces and parts that you're going to learn about. And the other organizations that are funded by this program, that are co-investigator institutions, and the other organizations include SAO, the Smithsonian Observatory, and so we wanted to include the great network of Affiliations museums in some of the education work we do. Another partner is JPL, and they do a lot of the exoplanet research that you're going to hear about. Sonoma State University, that also participates in the education work for some of the high energy astrophysics missions that you'll hear about. And IPAC, which stands for the Infrared Processing Archive Center. Yes, Infrared Processing Archive Center, which is the affiliated with the NASA's Infrared Spitzer mission, and you'll hear about that. So, without further ado, I'm going to pass the baton over to Brandon Lawton, who's going to kind of introduce you to the big questions of NASA astrophysics that the Universe of Learning is trying to find ways to engage the public in learning about.
Okay. Thank you very much, Mary. And it's wonderful to be here with you all digitally. Yeah, so I wanted to talk about really quickly a broad brushstroke over the science and the big questions of NASA Science Mission Directorate in terms of astrophysics. And I will mention really quickly, this is going to be sort of a quick little whirlwind tour. There are 6 more webinars that will focus on two webinars each on one of these individual questions that you see on the screen. So there will be a lot more content in the coming webinars, but this is just to give you some quick overview of these questions and how we address them. So the Universe of Learning focuses on the NASA astrophysics big questions, which you see on the screen there. How did we get here? Which deals with cosmic origins. How does the universe work? Which deals with the physics of the cosmos. And are we alone? Which of course deals with exoplanet exploration. And I should mention right off the top that NASA Astrophysics and our program deals with science beyond our solar system, okay? So just to give you some idea. Some of the current NASA Astrophysics missions, current and future, I should say, are listed in thumbnails on the bottom. These are just some of them, and we'll talk about how these missions work together. And so to start that conversation, here's just a little schematic of the electromagnetic spectrum, or the light spectrum. And we show this basically to give you a quick idea of why it is that NASA Astrophysics really needs all these missions. And so what you see here is a color-coded graph where on the left you have high energy gamma rays, and then as you go to the right you get lower and lower energy light. So you go from gamma rays to lower energy X-rays to ultraviolet, the visible light, that little thin one you see in the middle, infrared, microwave, and finally the lowest energy light is radio. And basically how deep or how far down those bars go tell you how far down actually that light can penetrate our atmosphere. So that's why we can have visible light telescopes on the ground, but if we want to get X-rays, we have to go to space, for example. Okay. So these just give you an idea that we have these different telescopes really to observe different parts of the light spectrum. All right, so why do we do that? Well, here's a really quick example. This is a galaxy you see on the screen here, and this galaxy is taken from various telescopes and missions in space and on ground. And this time just to confuse you, we've swapped the order. So now we have low energy on the left and high energy on the right. And this is the same galaxy, but taken in different light waves, different parts of the electromagnetic spectrum. So what you see, I'm going to start with the middle because visible light usually is easiest to talk about first. We're familiar with that usually more. So it's the type of light our eyes can see. And in visible light in that galaxy, you see all the combined light from the billions of stars in that galaxy. Okay, you see a lot of stars in the center of the galaxy, but the spiral arms are also composed of stars. So all the bright stuff are the stars. And then you see the dark stuff, which are dust lanes in the galaxy. Okay, if you move over to ultraviolet, you really see where new stars are being born. And if you move over to the high energy X-rays, you see some exotic things going on there. Those are the places where you have really high mass, dead exotic stars, black holes, really exotic things coming from the X-ray. Going the other way, infrared, that you see the dust glowing in infrared in the galaxy, and that's what you see there. And then in radio, you see the really cold molecular gas, which is the stuff that will later form stars, new stars. Okay, so that gives you an idea. If you want to understand an object like this galaxy, you need to put all the pieces together of the puzzle. And to do that, you really need to observe across the electromagnetic spectrum. All right, so let's deal with each of those three questions briefly. And again, we'll go into more depth in future webinars. First, cosmic origins. How did we get here? Really trying to understand how it is that humans got to be on this nice Earth in this nice, pleasant galaxy, the Milky Way galaxy, in our current state and time. And one of the ways to address cosmic origins is to understand where did galaxies, how did galaxies form? How did they change with time? Where did the galaxies come from? And so on. So I wanted to show you this. This is the start of what's called a deep fields, and it was started by the Hubble Space Telescope. And Hubble pointed at this patch of sky in December of 1995. And this probably doesn't mean anything to you because I have put nothing on here. So let me help you out. Put some constellations on here, and you'll see Ursa Major, or the Big Dipper part of Ursa Major there on the right, and the Little Dipper, or Ursa Minor, on the left. And what Hubble did was it stared for over 10 days straight at that little orange or yellowish box you see there. Okay, and this place was chosen because there was not much light or anything that other telescopes could see in that part of the sky. So what did Hubble do? What did the most sensitive at the time space telescope staring at that patch of sky for almost 11 days see? It saw this. This is called the Hubble Deep Field, released in January 1996. And almost every single point of light you see in this image is a galaxy comprising of millions of billions of individual stars, and probably millions of billions of planets and gas and dust and all the things that make up an individual galaxy. There are about 3,000 galaxies in this image. And this really put into perspective the enormity of our universe. To give you some idea, if you held up a dime at arm's length, and you looked at that dime, the patch of sky that Hubble could see at any one time is equivalent to the eyeball of the president on that dime as seen from arm's length, a very small patch of sky. And that small patch of sky is what you see here with 3,000 galaxies. In fact, it would take about 24 million of these to cover the entire sky. Okay, so this really blew open the field of these deep fields, understanding, oh, there's a lot to see if you can really peer back in the distant universe. So let's go forward and look at another great observatory, the Chandra X-ray Observatory. So Chandra did a deep field in the southern hemisphere, and it stared for about 7 million seconds over 15 years to get this image. And what you're seeing in this image, we've converted it to various colors so you can look at it, but these are X-ray signatures of supermassive black holes. Okay, there are about 5,000 supermassive black holes. And what we believe is that these supermassive black holes correspond, each of them, to their own cores of a galaxy. Okay, because we believe now that almost every galaxy in their core has a supermassive black hole. Okay, and so this is an amazing image that really took a lot of effort to put together. So this gives you some idea, 2 pieces of the puzzle, you're learning some different things. In visible, you can really see the galaxies of stars. X-rays, you can see some exotic phenomena like black holes. Let's talk about another deep field. This was a survey that's done by many telescopes called GOODS, or the Great Observatories Origins Deep Survey. 2 surveys, one in the northern hemisphere, one in the south. The north is centered around that original Hubble deep field I showed you, and the south is centered around that Chandra X-ray deep field I showed you. And this time, instead of just one telescope looking at each, a swath of telescopes looked at these across the electromagnetic spectrum. So you can see their little postage stamps on the side, but Hubble, Chandra, the Spitzer infrared telescope, the XMM Newton X-ray telescope, and the Herschel infrared telescope looked at these. And we can learn some interesting things. Here's an interesting result that we didn't realize before we did this survey. You look on the left, and you see on the left is a combined image of Hubble and Chandra. The 2 on the left are Hubble and Chandra images, where that faint, fuzzy, bluish stuff is the Chandra X-ray signature. I mentioned that we expected those X-ray signatures from supermassive black holes to be centered on visible light galaxies, but in this case, we can't find any visible light counterpart to them. We don't see where the galaxy is. Where is the X-rays coming from, right? Well, it took Spitzer to help us out, the infrared Great Observatory Spitzer. Okay, so it sees an infrared light, invisible infrared light. And what it found was actually where these were coming from, which are galaxies that do not emit a lot of visible light, or if they do, the visible light is blocked, likely because there's a lot of dust in these galaxies that are blocking the visible light, and the dust heats up and glows in infrared. So we don't see the visible, but we can see the galaxy in the infrared. And these are a whole different type of galaxy than you would see in the visible light. So really, we're putting the pieces together of these strange types of galaxies in these deep fields by combining the light from all these telescopes. And again, the end goal being that if we can understand the variety of galaxies in the universe and how they change with time, it gives us a good perspective of how it is that our own Milky Way came to be and how it is that we came to be able to exist within the Milky Way galaxy. Okay, so that's cosmic origins. I should mention real quick, cosmic origins, that there's a lot of future here in this area, and particularly in the deep fields. A couple of future missions, the James Webb Space Telescope and the WFIRST mission, are going to really help us explore this idea further. The James Webb Space Telescope is going to launch in late 2018, late next year, and it's going to be able to peer back even further in space because it's a really sensitive infrared mission. It's going to peer back even further in space than Hubble can. The WFIRST mission is basically a Hubble-class telescope, but it has a really wide field of view. And so what you see on the screen there are 2 deep fields taken by Hubble. Those little inset boxes are 2 deep fields taken by Hubble, 2 separate images by Hubble. And WFIRST is that funny Space Invader shape that you see there, that's the amount of sky it can observe all at one time. And so again, it's a Hubble-class telescope, but it can observe a large swath of the sky. And so we're going to be able to get all sorts of really beautiful deep images of these galaxies across the entire sky. And the WFIRST mission launches in the mid-2020s. Okay, let's go into a galaxy now. So now let's get into the physics of the cosmos. How does the universe work? We showed you, thousands of galaxies in these deep fields. what does a galaxy actually look like? Well, we can really look at a galaxy in detail if we look at one that's close by. So this is what you see on the screen here, an image, or actually over 400 images stitched together by the Hubble Space Telescope of our nearby Andromeda galaxy. This is the closest large galaxy to our own Milky Way, and it took over 400 Hubble images to put this together, but it's actually about 1/3 of the Andromeda galaxy. So there's a lot more there that you can't see. Okay, and you can see the core, bright core of the Andromeda in the lower left, and the outskirts sort of in the upper right of the Andromeda galaxy. Okay, and what you see again, Hubble's mostly a visible light telescope with some ultraviolet and some near-infrared capability, but what you see here really are all that light is from the stars in the Andromeda galaxy, and the dark things are the dust lanes in the Andromeda galaxy. But now that we can peer in detail inside these galaxies, we can start to look at how do the things in a galaxy really work? What are the physics of those things? So that can be stars, planets, gas, dust, and so on. So we'll do a quick example here. On the right is a composite image of the Andromeda galaxy taken from NASA's GALEX ultraviolet space telescope. And again, GALEX is an ultraviolet telescope, so it's going to show us regions where there's star formation or more energy going on there. And the New Star telescope is an X-ray telescope, and you can see if the inset, it's pointing at the core. There's this really bizarre object near the core of the Andromeda galaxy called a pulsar. It's called a pulsar candidate here, but we believe this is to be a pulsar. And pulsars were discovered almost 50 years ago to the day, so that we've only known about them for 50 years. And what they are the remnant cores of really massive stars. So as massive stars die, they shed most of their material back into space as a giant supernova explosion. And what's left is a core. And if that core that's left is roughly the mass of our own sun, okay, it's going to end up as what's called a neutron star. And I have an illustration of a neutron star on the left. It's called pulsar illustration, but it's also called a neutron star. And these neutron stars, again, are the core of what's left of these supermassive stars. They're incredibly dense and incredibly small. So they're the size of a city. Okay, so think of something the mass of our sun, but the size of a city, spinning really fast, several times per second. And the density is such that if you took a teaspoonful of this neutron star material, on Earth it would weigh about 1 billion tons, or about the weight of Mount Everest. Okay, so it's a really exotic type of object. Now, why do we call them pulsars? Well, the reason is because they're so dense and compact that their magnetic fields got compacted as well, and they have really strong magnetic fields lines, which you see in that pulsar illustration. Those blue lines are magnetic field lines. And where those magnetic field lines come into the poles of the star, it's funneling a lot of energy into the poles, and that energy gets shut off as light, high energy light, in two directions off the poles, like a beam. They're like beams. So as the pulsar spins really fast, if those beams happen to pass by us, like a lighthouse beam, we'll see that in it, and that's why we call them a pulsar. Okay, so all pulsars come from neutron stars, but we don't see them as a pulsar unless their beam happens to spin by us like a lighthouse. Okay, so very exotic objects. Just to give you some idea, there's only roughly over 100 that we've discovered in high energy light. So the Fermi Gamma Ray Space Telescope did an all-sky survey looking for pulsars, and what you see is the all-sky results there, where the brighter reddish, orangish, yellowish colors are the highest energy of gamma rays. Okay, the highest type of light, highest energy type of light there is. And the ones you see encircled there are pulsars. There's a wealth of other things that cause gamma rays that I won't go into here, but just so you can see that there's a wealth of pulsars on here. Most of them are in our own galaxy. That's not to say that they don't exist in other galaxies, but we haven't had the sensitivity to detect too many beyond our own galaxy. Okay, so pulsars exist in our own galaxy, and if we actually go to one that's famous, this is the Crab Nebula. There's the Hubble image on the left you may have seen before. This is, in the center of the Crab Nebula is a pulsar. So the Crab Nebula itself, that Hubble image, most of that light you see is from gas and dust that got sent out by a supernova explosion. And if you look in the center, you'll see the pulsar. I'll just play a little video. Here's a pulsar video. On the left is Chandra X-ray, and on the right is Hubble visible light. And so you can see sort of over a span of a year or so, taking snapshots of this pulsar, they can see the actual energy emitting out from that central pulsar from the Crab Nebula. Okay. All right. So for sake of time, I'll just end with, why do we care about pulsars? Well, one of the reasons is because pulsars are a very exotic place where you have such high densities that you can study things in that high density that you couldn't study really on Earth. And so we get sort of a sense of what happens in the physics of the cosmos. I'll just end with, there's a NASA mission called NICER. It's an X-ray telescope that's actually just launched in June. That's on the space station. And it is looking to actually understand the interiors of these pulsars, what's going on in the interior. That's a big mystery, and that's something that we want to explore further. So you'll hear more from that, and you can see this video play here. This is an animation of a pulsar over San Francisco, and then you can see it spinning. There are the jets, and then it's going to do a quick cutaway to sort of give you sort of an idea of what we think the inner part might be, with a gigantic question mark that we want to figure out for the core. So a big area of exploration of the physics of these objects. Okay. All right. So I want to end with Are We Alone? Exoplanet Exploration. We talked about pulsars. What about planets in our galaxy? Okay, so that's a big area of exploration, and NASA is very interested in that, to figure out, can we find habitable planets? Could we even find life in the universe? So I'm going to just end with this topic with saying that I'm going to show one type of way of detecting exoplanets and one type of way of studying them further. But there's a wealth of other ways that you hear about in later webinars. So the primary method that we've detected most of them is by this transit method, where as an exoplanet goes around its star, if we happen to be lined up like this, where we can see it edge on, and you'll see in the lower left the graph, as that planet passes in front of that star, we don't see the planet directly, but we see the starlight dip because the planet blocks some of that starlight. And by catching those dips, we can determine that there's exoplanets there, and maybe even, things like the size and so on of those exoplanets. This has been done by Kepler. The Kepler Space Telescope has done most of this. You can see a schematic of our Milky Way galaxy on the right, and the Kepler search space is that little cone of light there that goes out about 3,000 light years in one direction. All right, so Kepler used this transit method and stared at about over 100,000 stars for several years and discovered about 4,400 exoplanet candidates, of which more than 2,300 have been confirmed to this point to be exoplanets by follow-up observations from other telescopes. And so I will point out that the point of the Kepler was not to survey the entire galaxy, because that would be hard, but to really just do a census of our galaxy to get some ideas of numbers. And from the Kepler survey, we now know that there should be roughly 1 billion Earth-like planets just in our own galaxy. And when I say Earth-like, I don't mean that there's life on it, but I mean that the planets are Earth-size, probably within the habitable zone, the place in their star system where liquid water can exist. So they may be habitable. So they're great follow-up candidates for further study. And I'll just mention that there's a mission launching in 2018 called TESS that is going to do this survey of the nearby universe. So here's a zoom in on the right of the Kepler field again, and you'll notice a little crosshair with the red circle around it. TESS is going to survey over 200,000 stars, but just locally over the whole sky, so within 200 light years of us. And these are going to give us sort of the nearby good candidates for follow-up studies of nearby possible Earth-like exoplanets that we can follow up with other missions. Okay, and then I will end with this slide, which is to say that once we know that they're there, what do we do, right? How do we know that they might be habitable or interesting? And I'll say that a wealth of missions, including Hubble and Spitzer and James Webb when it launches, are doing these follow-up studies of these candidates that Kepler finds, that TESS will find, and so on. And one way that they do these follow-up studies is what's called transit spectroscopy. It's a similar thing. Edge on, the exoplanet passes between us and the parent star. But this time we're not looking for the dip of light as it passes in front of the star. What we're looking for, as sort of illustrated in the bottom plot there, is that as the starlight passes through that exoplanet atmosphere on its way to us, we can break up that starlight into the individual colors, and any colors that are missing tells us what materials were in the atmosphere to block those colors from the parent star. So in the bottom example, those two lines of colors that are missing correspond to sodium. So we know sodium's in there. So just to give you some idea, some Hubble, Spitzer, and other telescopes have done this already for a few exoplanets. We found water, we found methane, we found various things in some exoplanet atmospheres. But it'll take James Webb to search for Earth-sized small exoplanet atmospheres. And I think with that, yep, I am done. So I am going to go ahead and turn it over to Tim Rue, who is going to tell us about some connections to resources.
First, we do want to give you guys a chance, if any of you have any questions for Brandon before we let him run away, please put them in the chat. We can also we may be able to have someone unmute and ask their question aloud as well. So please let us know. What would you like to know more about? If you don't have questions right now, or if you're still thinking of them, please go ahead, stick them in the chat, and we can always come back to Brandon later, but we don't want to leave everybody hanging while folks are thinking. But please, Brandon has been, there's a question for you, Brandon. What would it take to detect biomarkers in the atmospheres of exoplanets?
That is a great question. And I'll briefly answer it here, but later in this, Eric is going to tell you about the community practice and the Moodle and how we can address and have conversations there, and I will put more information there. But to say biomarkers are signatures in the atmosphere that can tell us that life is actually there, and it's very hard to do. James Webb, the goal of James Webb is not necessarily to find biomarkers. Even the power of James Webb may not be able to tell us definitively that there's life in those exoplanet atmospheres. Although if we get lucky, it may. It's going to take something an even larger space telescope. And I will tell you, James Webb was initially conceived in the late 1980s, early 1990s, and it's now just launching. We are already thinking of the telescope to come after WFIRST, the telescope for the 2030s. And several of the designs for that big telescope are to answer that question. What does it take to actually detect definitively biomarkers in the atmospheres of nearby Earth-like exoplanets? And so that is an active area of research. And so the engineering community and the scientific community are coming together to figure out just that answer. So I guess I'll just say we'll do more of the conversation on the Moodle, and there's more to come from that, but that's a short answer.
Brandon, can exoplanet spectroscopy identify water or just hydrogen and oxygen separately?
That's a great question. It can identify water. We have identified H2O. We have identified water in several exoplanet atmospheres. Those have mostly been as water vapor, and they've mostly been in giant Jupiter-sized exoplanets in their upper atmospheres. To actually do that in an Earth-sized exoplanet, that is something that hopefully James Webb will be able to help us with. Yep, James Webb will help us there. All right. These are great questions, by the way.
So that was a great introduction, Brandon, to like these big questions and exciting areas of discovery of universe of learning. And as he mentioned, we'll be exploring those more in future sessions. But at each session, in addition to getting a little taste of some exciting new discoveries, we also want to introduce you to resources from the universe of learning. And so Tim, I think, is going to walk us through a few key universe of learning resources.
Yes. So one of our big goals here is not just to teach you about NASA science, as fun as that is. We want you to have the ability to take the science that NASA collects every day and be able to share that with your own local audience. And hopefully you'll be able to take some of these resources, these images, these activities, these videos, these exhibits that we've created over the years, and we're still creating new stuff for you now. You'll be able to to take that and find a unique way to use it with your audience, and we'll be able to hear about that. So today I'm going to introduce you to just a couple of the big ones, and the first one I'm going to show off to you is NASA Wavelength. This one, just a second, I'm going to take over the screen share. So wavelength.org. So this is a site created and maintained by NASA directly, and anything that you see on here has gone through an in-depth product review process. It's certified 508 compliant, so you know it's going to be accessible, and there's some really amazing stuff. And just to give you a little bit hint of some of the sorts of things on here, there are a couple different ways to explore this site. You'll notice down here, a little bit down, there are a couple different audiences. I'm going to look into the informal education one, which feels a little bit appropriate for you folks today in just a moment. But you'll also notice the top, there are some individual resources. These change all the time, the ones that they've got highlighted. Right now, there's a lot of focus on the eclipse, also the Cassini mission, which is ending in about a month. But we're going to jump down and look at some resources themselves. So informal education. Again, those highlighted ones, you can see the eclipse. And there are all sorts going up and down, hundreds and hundreds of resources. If you look at one individual one, you'll notice a little image giving a little bit of a clue of what it is and a description of the resource. And you've got a couple options. You can look at the resource details. I'll do that right here, where you can get more information about the resource. You can find ways to share it. You can find other things that connect with it. If you would like, instead, you could go to the resource. So this one, Women in Science, was created by the Smithsonian Astrophysical Observatory. And down here, you've got, these are a number of posters focused on women in STEM. You've got astronomers, you've got astronauts, you've got scientists, administrators involved in NASA who over the course of time have helped advance our understanding of the universe. So you can download these and use them for yourself. And if you scroll up, there's a little bit more information on this page about all sorts of things. So this is just one of the many, many things that is found on the NASA Wavelength site. You also have the opportunity to add these to a list. So say you wanted to put together a list of resources that you wanted to share with local teachers in your area. You could use NASA Wavelength to go find a bunch of resources, add them to a list, and share them out. You can also find other lists that other people have shared. These actually are one of the best ways to go about finding resources through NASA Wavelength. They're curated lists for you. So say I wanted to find something about a galaxy. I could look in here. There are 4 different resources, or 4 different lists, each of which with a bunch of different resources on galaxies in here. One of them you'll notice is was done by Brandon, who you just heard from for the Universe of Learning Science briefing. Some of you may be familiar with that. Other ones may not. That's all right. But we've got a number of different things. One more thing I'm going to point out on NASA Wavelength. Oh, and I should add, when you go into these lists, there are resources that are listed on NASA Wavelength that have gone through the NASA product review. You also have the opportunity to add in links to external resources that haven't gone through the whole product review process, in case you're making a list for yourself. But one more place I want to show you real quick is the data and images link at the top. And this has some really awesome things. You can go and find pictures. You can find data about all sorts of different things. There are these lovely little icons on here. You can see this one's about Earth. There's stuff about the moon, the sun, planets, the universe as a whole. And it's got them broken down into intro, intermediate, and advanced, so you have an idea of what you're looking at. Some of these are from us, from the Universe of Learning, for example, Astrophysics, which I'm going to talk about in a moment. Other of these are from other places around the country that have NASA images or data to share out. So this is a great place to explore on your own and get an idea of what's out there. I am going to jump back to, oops, actually, I want to jump back into this show. and go through just a couple other really important resources that I think are important for you guys to know about. The first is this Astropix that I mentioned. This is a collection of NASA images of the universe. There are nebula, there are galaxies, anything, and actually includes stuff inside of our solar system as well. So anything that a telescope in space may have taken a picture of, you can find it here. There's some ground-based stuff too. But these are all, they have all sorts of metadata, some tags associated with them, so they're really usable. You can find out what wavelength the picture was taken at. In other words, what type of light. Is it an X-ray image? Is it an infrared light image? Is it a visible light image? You can find out where objects are. You can find different resolutions, different sizes, and these are all images that you can pull and use for yourself. There's a great search feature on there. We'll be talking about Astropix a little bit more in the future. But this is a great place if you happen to need pictures of anything. You can see the website there, astropix.ipac.caltech.edu. And these resources I'll mention as well, they're all listed on the Moodle, which Erica will be talking about in just a couple minutes, so you've got easy access. You don't have to scribble these down right now. The next one, Eyes on Exoplanets. The Universe of Learning has put together a number of exhibit-related materials. Eyes on Exoplanets is a digital exhibit resource that's being used in a few museums around the country already. It's a chance to actually go through and explore our galaxy, the Milky Way, and find exoplanets that we have found. It shows you where they are, what their systems look like. You can rotate them around, you can explore, you can make them move. They've got these wonderful artist impressions that are really beautiful and give people a sense of what is out there. You can check this out, play with it on your own computer. You can also look into putting it into a museum or as part of an exhibit if you're interested. ViewSpace is a video product. It's about 200 different museums, libraries, science centers, other places around the country. It is actually, we've got a new updated version of ViewSpace that should be coming out very, very soon. I'm not going to put a date on that, but we're hoping in the next month or so. That you will be able to go to viewspace.org and get access to this for free. Those of you who have it already will be transferring you over. So this is just a little sneak preview that you'll be getting some extra benefits from this. This is a video product that shows awesome images of the universe, amazing information related to that. It explores them. It's this really restorative experience to have in a museum and a chance to learn new information. And it's one of many video resources that we have. I'm just providing it today as one example. You can check it out online, and we'll be talking about it more in the future. The final one I'm going to mention today is just one more example, Recoloring the Universe. This was done by Chandra and SAO, Smithsonian Astrophysical Observatory. This is a chance for people to learn about coding, for kids to learn about coding while they're working with astrophysical images. They use actual computer coding techniques that they learn over the course of the program. This has been done in person, it's been done online, it's been taught to librarians. We've worked mostly with libraries on this to actually deliver the material themselves. So this just gives you a little bit of a sample of the resources that you're going to be seeing over the course of these webinars, and we're excited to see what you can make of these and how you can take them and do something new with your audiences. So now I will pass it over to Erica, who's going to talk a little bit about the Moodle, the way we will be progressing through the next few months.
Great, thanks, Tim. All right, so to show you guys where you can find all these resources, I'm going to give a quick tour of the Moodle itself. So I'm going to share my screen now. Okay, so hopefully everyone can see my screen now. All right, so the link that I sent you should bring you to this page here, the Universe of Learning. Get a little background here. There's a couple places you can log in, and there's a little login button towards the upper right-hand corner up here. You can also just click right on the center here. In one of my accounts. On 1 second. No, that's not typing. Okay. So you should have all received an account from me already. If you haven't, please contact me. Maybe Mary can put my email in the chat box so you don't have an account to the Moodle yet, send me an email. We'll make sure to get you online, okay? So a brief introduction to our Universal Learning Community of Practice here, so you can navigate. Over on the right-hand corner is a list of upcoming events. So right now we have our next upcoming webinars here, which seem to have gone a little funky on their time. They're all at the same time every 2 weeks, so I'll double check on what's going on over there. A couple other key things you're going to want to look out for. We have 3 different discussion forums here in the portal. This top one is news and announcements from the team. So anytime we have an update that we think you should know about, perhaps when USpace comes out, Tim will send a message out, or some member of our team will let you know that that's now available. So anytime you're going to hear from us, you'll get a notification there. You'll also, if I can move my images to the side here, get a little notification in the bottom right when you log in telling you there's a message you haven't seen, okay? Any emails, any notifications that get posted here will also get sent to your email, so you'll know to come check the Moodle for that. We also have this Affiliations forum here, and that's more of a space to have programmatic questions and discussions. If you want to know, if you, for instance, forgot when the next webinar is, you can ask us here and we'll get back to you right away. This other one is a really important one, our weekly discussion topics. So in between our webinars, we're going to be holding discussions about what we discussed each week, all right? Inside, this coming week, your assignment's going to be to tell us a little bit about how you currently engage in astronomy and astrophysics at your institutions. We want to know more from you so we can better provide you materials. What you want to do is just click on discuss this topic in the bottom right-hand corner, and you can then reply to that stream. So every week, a new discussion topic will appear in that box there, okay? You can also start your own. Just if you have a specific thing you want to know and talk about, you can add your own discussion topic up here as well. There's also these little breadcrumbs that you can use to get back to the main page. UoL will bring you right here to the center page. So all of those things that Tim highlighted today are right here under some of our highlighted UoL resources. These are some of the things that we think are going to be most useful to you throughout the program. So like he said, NASA Wavelength, you just click on that and it'll pop up right inside. Some of them also pop up as an external site as well. Finally, another important thing is the recorded webinars. In case you happen to miss a session or you want to go back and see something that we said, each week each session will come up here in these unavailable. So as we go through, they'll be added to it. You'll be able to click on it. By tomorrow, this recording will be available right here. You can also click right here to see the slides, and the highlighted resources will be available below. And then finally, at the bottom, it's a whole slew of extra resources. So as you can see, we've got classroom activities, digital exhibit components, exhibits for your spaces, all within here that we really encourage you to explore. There's lots of wonderful resources. Here, view space is available in here, eyes on exoplanets, all within the Moodle. So you don't have to remember any of these URLs, they're all there for you to have access to. All right, I think that covers most of the major components of the community of practice that you'll need to know to be able to be successful here. We're gonna go back to our slides, just to give you a sense of where we are and where we're going the next few weeks. Today we had our introduction to the community of practice. So all the things to give you an idea of what's coming up. In 2 weeks, we're gonna have our next webinar on how does the universe work. Mary's gonna give us a tour of the universe. And actually, do you wanna say a little bit about the tour of the universe that's upcoming?
Sure. Yeah, so on the 30th, we'll kind of take a historical and virtual tour through our knowledge of what's out there in terms of stars, our Milky Way, galaxies, and the universe. So we'll both take a look back in terms of how we found that. We know a lot of you are from history museums, and that might provide a hook to NASA astronomy context, and that you'll bring your own insights to the content as well. So I look forward to seeing you on the 30th. If you want to go back there, thanks, Erica. Yeah, so as we go forward every couple of weeks, we'll explore those big questions that and some of the discoveries that Brandon introduced, along with resources and ways of exploring those kinds of discoveries through different kinds of activities and resources each time. And then in November, the opportunity to apply for the mini funds to implement a program will open, and we'll be talking about that more as we go along with the specific date and the application process. But as you know from the informational webinar, one of the key parts of this community of practice is that we hope that you'll go on to imagine ways that you might engage your audiences and apply for some funds to do so. So the next steps are for you to say hello on the community of practice, explore it and its resources. Let us know what other information or kinds of things you were hoping to get out of this community of practice, and we'll see how we can meet those needs. I feel like there's, well, let's stop right now and ask if there are questions at the moment.
I'll just note that in the chat box there were some questions about Q&As from the webinars being listed as well, and I wrote in some responses about the discussion boards. We'll be having some discussion of science questions in there. We'll be having some guest scientists and astronomers coming in and participating in those, plus Brandon will be there very regularly. And we will also be able to answer other sorts of questions on the discussion boards as well. Whether they're about resources or other things.
To go along with Tim, I'm also monitoring the questions, so just in case any answers don't get, any questions don't get answered, or this is something that we don't want to quite get off topic. I already spoke with Erica, and we will put that on the Moodle, just a transcript of what was questioned and what was answered.
Great. Thanks, Patty. If there aren't any questions out there, I am going to put one little link in the chat box, which is a quick feedback form. It takes less than 60 seconds to fill out, but it'll give us some sense of course corrections that we need to make to help make these meet your needs better, and you'll have a chance to just comment on that. So we'll also put that link on the Moodle on the community of practice, but it's right in the chat box. If you were to click on it now, you could it's a little anonymous feedback on this session. So I think we want to thank everyone for joining us. This was wonderful to have so many participants from around the country, and great affiliate museums and organizations that we know have lots of unique ways of engaging your audiences. And so as we go along, we're really looking forward to hearing from you more about ideas that come to you as you learn about what the universe of learning resources are, ideas that come to you for engaging your audiences. So with that, I think I'm going to